First question, just a warm up, say what you thought of the hackathon. It seems there's a kind of consensus answer. In Salt Lake City, one of the big ones was hungover. That is sexy.
What's that?
So
You don't know that.
So for each team, after they presented, a new question is going to appear, and it's going to ask you to score all the teams on 5 different categories: their originality, how novel the idea was; functionality, what got done; the impact, is this commercially realistic or interesting; teamwork, how well did they work together in running the project; and then design, how well executed and presented was it overall. So everybody can vote for every team. You can vote for your own project as well. But I can keep track of how many people have voted. So I'll be, if the numbers start tailing off, I'll be encouraging people to crack on. Now, we're going to use a Wheel of Fortune to select the teams. Now, you might think that the first one's a bit of a setup, but that's because Team Geo Go literally have to go. So without further ado, put your hands together and we'll have a presentation from Team Geo Go.
There we go.
When do you start? So I have only 2 hands. This is our team. Super. This is a mobile phone. I love Pokemon Go. This is a very valuable piece of geologic information. I would love to see. Geologic information as picture on a device like Pokemon Go in any application, oriented spatially. So XYZ picture, anything, plot, data, save slides, and of course, I had over 50 levels.
So we decided to try to create a sort of, or maybe not. Ah, there it is, amazing. So we try to implement this idea as a kind of concept in Python. Very kind of success with that. And we decided we wanted a map where you could look at map and then find interesting areas where we had data. So we created a Google Map view where you can go in and press a marker, get, for example, a well trajectory, find interesting segments in that, and press, for example, Pikachu, and you get the well course. And although this was interesting to work with, it's not very fancy. So here's the man that makes it fancy.
Fancy-ish.
Yeah.
No signal.
I should wait a second.
Yeah.
Hey. Right, so as of yesterday, as we mentioned, we're having some difficulty in coming up with a design that we thought was going to work. So the idea was to run 2 parallel activities. One of we failed to build something, and one if we were successful. So the successful one is what we just showed you, the only, but one of the ideas was to have a mock-up of what we wanted it to look like. So we took a 2D map, as you can see, and then provided some depth to that map. So as you can see here, we've got the well paths and some of the actual core samples and the pictures of those, the images which are geo-referenced against the core sample. So we've done some bodging, geosurface scale and depth as well as you have. But as you can see, one of the bonuses of this is the fact that you can zoom around and also add additional information, georeferenced information, which is also suddenly just moved. Okay, so we can start looking at horizon data, seismic cubes. So in effect, we can connect to any spatially referenced database. We've got 3 minutes and 19 seconds. 19 seconds again. AI. So one of the things we're going to follow on from this is the fact that we can have, start looking at the actual images themselves and do some machine learning and maybe quickly 3 seconds and do some referencing between them and some interpretation. So, I'm guessing I've run out of time. So, any questions on the judging team? Or anyone else for that matter? This is open to all of us.
Yeah, so question. So some of the stuff you brought before the weekend, what was done specifically during the weekend?
Everything.
This tool?
The tool was provided by Vizards, so that was a Power View, which is an excellent tool, but it's just a visualization tool. And visualize.
No much Python. No idea. Completely fresh, completely new.
But this has all got the ability to input Python. So 10 years link.
So from scratch.
Who else?
We brought Core.
We did the 3D photograph stitches.
Yeah, we actually discovered that it's not possible that the 3D and 2D do not match format-wise, and that there's no possibility to actually attach XYZ to a photograph to orient it spatially. And we think that could be really valuable because there's so much geological information that a photograph could really enhance the information.
So we can do a book around. You can see in Google Maps, we can't put those around. So that value, the negative Z value was a real challenge for us. We could have faked it, but it wouldn't have we've had to fake all our other data to match it, and it's just confusing. So Barney did a great job in being able to
also,
represent that for us.
Pokemon Go is only surface, not subsurface.
That's it.
So guys, got any mobile phones? We've got 12 votes in some time. We'll have till the end of the next presentation to vote. If we get your votes in as quickly as possible, that'd be great. Okay, so now comes the fun part. So the next team to present will be the blind spots.
Ready? Hiya, we're the blind spot team. If you remember, we were looking at data quality, and we are a ragtag bunch of people who've never met before or even heard of each other on Slack, apart from myself and Laura, who's one of our Teradata data scientists. We've got other people with subject matter expertise, Python skills, and lots of opinions. So, what did we do?
So, as Doug's already said, the problem was to try and find some way of visualizing log data so we could try and assess the data quality much more effectively. So at the moment it's a fairly manual process, looking at lots of files and there's not particularly visual. So we were looking at whether we could have an improve the efficiency of the process using visual tools. So if you haven't already done already, we've basically put together a cloud-based data quality platform which basically lets you receive data and have a very quick QC and take your data quality process from there. And I'm going to hand over to Sean, who's going to give you a demonstration of what we've built.
Yeah, so if you want to play along, use your phone, scan that QR code, and go to that website. I won't leave it up there too long, so we don't have too much time. Okay, everyone's done. I'll just need to go. Okay, so we implemented this on the cloud using AWS. So you go there. This presupposes you've already done the heavy work of going through a whole bunch of LAS files and stripping out all the data that's common and dealing with weird mnemonics and things like that. And you can, oh no, is that happening?
We have the screenshots because this is the first time this happened today.
Bloody hell, I was working when I was sitting down. Okay. Here we go.
Fine downstairs.
So this is what it would look like. So you go to your landing page and you click on QC stats and it'll go through each of your wells. It'll tell you how many files are in that directory, how many LAS files, if you have PDF files that have other information. Text files, we had tops and bottoms of formations, which were in text files. So this can just give you a quick idea of just knowing what's out there. Then after you've done some work in the cloud, you can image your data for various wells. These drop-down groups can switch between gamma and resistivity, choose a group, choose the whole well, choose the well, it produces some stats here. This looks kind of wonky, and that's because there's probably two different runs that were done on the same part of the well. So you're getting two resistivity values at each point, and you can quickly say, well, you're following the same pattern, but the same. Sometimes they'll be one's way off, and that'll give you an idea that there's something wrong. So basically, it's a quick way to do this. If you try to do that in Excel, you might never bother doing it.
So the idea was when you're during contract, it gives you some new files, comes in the landing area. You're a busy data manager, you're out on the ski slopes or whatever, you want to know whether to push it back and say, please fix it now, or can you bring it into your data architecture, can you do the masking, can you build your dictionaries, is it fit for purpose? Can you land it in some kind of contextualized way to see whether it makes sense against all the other well data you've got? We've used a whole load of open source tooling up here that is common across the developer community, data managers, and the domain users that have to use it at the end. Any words from the data scientists?
I just want to add that we will hopefully get this up and running very soon, so you can actually go and try it out. It's in GitHub under the MIT license, so feel free to modify it at whatever.
You learn a hell of a lot from it. Very good stuff.
Hi, great job. Did you guys make any consideration for versioning of data? That's a big issue of looking at multiple files that might be the same log or something and how to work out what the provenances and quality. That's something you had time to consider?
It's on the left-hand side of the camera.
Very good.
Yeah, it was a huge issue, and that's why we quickly said we're just going to go through and grab the first thing that says home, and that's resistive. But we know that they're all very different in multiple ways.
And then you get difference between NWD and wireline logging as well, so that was something else people wanted to build into.
Yeah, those could be extra drop downs in the future.
So we're going to build a startup around it and put all that in, so it might be
Yeah, I have a question. How did you work as a team?
Yeah, so I did a lot of the grabbing data from the last files and playing around with them and outputting them.
And kind of spent some time looking at the geological data and making sure that it made sense from a yeah, I guess they kind of people start putting the window kind of us that have then caused a lot of things wrong with the reading.
I spent a lot of time making the OK visualization work.
And I would say that I learned from our subject matter experts who know about this data that I have no idea about. So I learned about what's actually relevant to put on this QC page, and then together with Kristen, we made this program this with that, and then put the stuff in there that seems to be relevant.
But also put all the text together on AWS. So 2 minutes.
And the next thing is the volume uncertainty is visible. So voting is now open for team 2, so place your votes in matching to the team 2.
Hi everybody. So we call ourselves Fortuna, and we are 6. And as you might see, we're all geoscientists. None of us really hardcore developer or coder, but nevertheless, we're all concerned by the uncertainties on the volume that we can have inside of Earth. And here we were focusing on our sketch, the synthetic data. So we have the top horizon, bottom horizon, and we have the oil water contact. So what we are concerned is the oil volume here. And you see that each feature, like top, bottom, and contact, can be uncertain. The position in depth will be uncertain. So therefore, the hydrocarbon column height will be uncertain, and the volume that you will have and that you will produce after will be uncertain as well. So we were considering how to visualize it and how to help people to understand uncertainties. First of all, the very basic, it's the GRB distribution. So this is the CDF. You can choose any values, and you can see how your hydrocarbon column height is varying depending on the volume that you obtain. Then you can cross-plot your volume against any parameter. In our case, it was oil-water contact. And again, you can see how your hydrocarbon column height is varying, because it's very important when you are estimating the cap, the integrity of the top layer, sealant layer. And again, one of the features, it's interactive and it's moving. So it shows you, depending on the volume, which minimum, maximum, and in what case for the hydrocarbon column height. Another type of visualization, obviously, it's section and maps. So here we have a well position where on the section and on the map in color, you could see the probability to be within the reservoir. And in white lines, it's one of realization that was calculated. Yeah, I forgot to mention that the statistics was run on the 200 realizations of top, bottom, and fault. And as you might see that we are fading a bit further from the well, so we become more uncertain, and you can compare the particular realization with the uncertainties. So one of the other visualizations, it's actually about horizons position themselves. So here you have in same colors, but this is the entropy, and you can see again the well position. We have no uncertainty on the well horizon because we know where is the horizon we drilled it. And when you are going further, you can see the variation, and you can see how position of your horizon can be uncertain. The same with the map. So our application allows you to see how volume is impacting the different how to communicate height, etc. And you can visualize it, especially to see where, for example, if you want to put the well, where it's better to put the well to be within the reservoir, but at the same time to have less uncertainty on the horizons, etc. So this is it.
Very nice. The data set that you present is derived during the weekend or?
No, the data set was prepared, so we have 200 of visualization of the map of the top horizon and bottom horizon, and we had the table which corresponds, like for example, the GRV volume, the oil water contact for each realization. So this is the synthetic data basically that I use at work, and I decided that the important thing was here about the visualization, not the computation. So the computed data, we can chat after how it was computed, but it's not the point here.
Sorry.
Yes, of course.
Yes, one question. You all geoscientists know developer code here.
No.
So how did it feel and how did you use the software code?
Well, we have several specialists here. We have a specialist in entropy. The code was in Python, I suppose. We have our guy who actually visualized everything that we've done. And this was initially the web page. And we have the guy who was, let's say, responsible for that everything moves smoothly. So with the slider and so on. And we have the specialist on the cross plot on the distribution, and we have also the specialist that provided all the statistic data for the probability to be within the reservoir, etc., etc. So there was Python there, and I was trying to help them to. I was not coding, but I was trying to help to find people with somebody stacked or something.
Question here. How do you see that being implemented in the decision-making process? Have you thought about that?
Yes. So this is the probability data. So you have in here, for example, if you need to run the full analysis of uncertainties, so you need to let's say extract some realizations from the GRB realizations and put it further for a geologist or for an engineer. You can actually, that if you want to extract realization that doesn't look very different from the base case, but still within the volume or within the probability of your cloud, this visualization would help you. And if you want, for example, the next visualization with the entropy, it shows you how your horizon is going upward or down. And in next version, if it would be next version, ideally we will need to connect all the graphs. So for example, if you choose one realization for volume, it shows you how it looks like on the sections, etc. If I answer the question.
Yeah, thanks. Thanks a lot. Great. Very nice.
A couple of people have asked what the code is for the voting. The voting's open for team 3, last team. So go to menti.com, and then the magic number you need is 937316. Yeah, let's see who's next up. It is RGBlend.
Ready? So good afternoon, everybody. So we are the RGBlend team. We are a mixed team between the people from Kinor and some people from Total. So Jack, maybe you can introduce yourself.
Yes, I'm Max. I'm a geophysicist.
Hello, Georges. Jürgen, and I'm a programmer. I'm Jonathan, software developer.
And I'm Melanie, I'm a Java developer. So to make a long story short, our topic was concerning these three images, and mainly, can you immediately spot the differences between all the combination of these three images? So to deal with this topic, we had a plan. Super nasty. But mainly, we split the work between making RGBlend. So we have to design a transfer function, which has been done by us. Olaf and Jürgen find data because we have more data. And John and I work on the web app with design. So I let Max talk about the technique.
Yes, so again, it's this topic, we have to find the differences. And of course, we voted as awesome before, so make sure to do that again. Okay, so basically what we're doing, quite quickly, we developed the code base, and then just to test it out, we made a web app, which is, yeah, okay, but which is basically taking one of these images, the grayscale colors here, and blends it into an RGB. And it takes out basically the alpha information, which is the achromatic information, because no one needs that anyhow. And basically it is able to plot all of the data onto this ternary diagram. So actually, for the first time, you can actually see where your data plots in it. And equally, you know, we can just test if it actually works properly. Don't worry, we also wrote a test suite. And actually, you know, normally, we came up with this originally, is that when you are in NumPy, in Matplotlib, or anywhere in Python, you want to have easy access to this. So traditionally, you know, I am shown, and we sort of modeled this according to this. So if you just import RGBlend, and you have a wrapper for importing the images, and actually then you just run this, and it does this. So it's quite easy access to quite a complicated function. And so for these three images, that's kind of the solution. You see that the guy moved here from this to that, and you actually, okay, it's white here, but you see these channels basically, how they contribute in here. Of course, you can have a similar example, which is just, okay, this is executing the same stuff again, just with three different images. Here you have a cactus. Maybe you have something else, I don't know what that was. Oh, sticker or something. And you put this into these three channels, and basically you can see how it plots here.
So, what are the use cases for that stuff? So, in oil and gas, there are several use cases. You can use that for 4D, for instance, you've got several seismic at the same zone for different time, and you want to compare your section. You can use that to identify the structural difference between your seismic. This is one example. Another use case would be, imagine you've got oil leak at the surface of the sea, and you've got lidar acquisition, and you want to follow the oil at the surface of the sea. And just using it, you can see how the oil is moving on the surface of the sea. And sure, there are a lot of applications in other domains.
So what do you see as the next steps for this?
Clean it up.
There is a test group.
Yeah, it's a little bit like code-wise cleanup. It's also horribly slow.
And we had also a lot of ideas for interaction on the web app because we tried to implement a following cursor on the blended image and report it on the small thumbnail that didn't work. So but we had other ideas for interaction.
Also, for example, if you had more interactivity on this, you could might select certain color ranges and then update this image to just isolate.
Which pretty much you need to step up the feature game on the library itself, because right now it's very bare bones in order to showcase this exact area.
Could you use a kind of an inverse function to align images?
Yeah, I think that's a bit more complicated. If you want to make an analogy of what this should mean sort of in the greater context, is if we have a cross-plot, if you have just two vectors and you cross-plot them, you do that in order to see a correlation, right? Maybe. And that is just a quick visual check, is there a correlation or not? And this is similar to that. So this is not really analytical, calculating certain metrics. It's more like to get a visual impression of what's happening and to combine, of course, three maps in one.
It would line up differences quite significantly, and then we can probably tune like thresholds and what would contribute to colors or not, which you probably be able to tune a little bit in better as well. So quick check, I guess.
Any other questions? Thank you very much. Okay, the judging's open for team 4. And the next team up will be this is a fun one, AR Sandbox.
Too many samples. There is on the table. Yeah. So you can Simon and you will then check it out if you think between you two, just with you're gonna start that okay, almost done. We are mirroring. It's mirroring now. It's mirroring. Yeah, emerges.
Okay, we should get started, I think. Yeah, ready? All right. Yes.
Yes, welcome. We are two teams that work very closely together on this sandbox, and we have 4 geophysicists that work on the 2D wave field propagation modeling, and we have the guys from Scotland that work especially Germany, Aachen. But yeah, oops. But I'll just introduce you.
Yeah. I'm Simon, so I'm also from Aachen, but most of the team, except for Anton, he's from Denmark. And yeah, what we built mostly at home is this augmented reality sandbox. And some of you maybe have seen that in an exhibition somewhere. It's there are different ones around. Usually what they do is they just plot topography. What our sandbox actually does, it renders the geological model, so actual underground data, into a sandbox that you can shape with your hands and define the topography. And it's actually running right now, so what we can do is we can shape the sand as we would, and what you see is the underlying model is adapting, and you see the geological map actually changing. So to the left there's fault, and you can dig your hands in and get dirty and be just like the god in the field, basically. So we used the weekend to develop it quite further, and I would just hand over to Miguel. He's walking you through the features we implemented.
Okay, so now we are going to show more or less all the features that we have done, and we have put most of them together. Some of them we were not able to add it to the main library. So the first thing that I did is making multi-threads, so we don't stack the kernel when we are running the sandbox. So we have access to the Python logic, so we can make all the rest of the steps. So one of the features that I'm not going to show for time is that now we can change also the underlying 3D model and see how the geological map changes in real time. The next thing that we did was the detection of sources using Lego blocks. Maybe you can put them.
Yeah, and explain. Can you just show the camera?
So this one should recognize. Is it actually recognizing? Oh, in there, yeah, it recognizes different shapes. We use Lego pieces now, and then you can use different shapes. Here we program that circles should be recognized and use that as markers, for example, for sensors or for emitters, and other shapes would be other things. So you can use that as, you can see on the right that it actually recognizes the marker, those two. And then we want to use that, for example, for something that Alex implemented.
Yeah, so basically we also implemented that when the code recognizes the 2 points, it automatically draws a section, as you can see on the drawing he's doing, because he has, you should show that.
Yeah, I don't have the plot rendered in the notebook. It's there, so basically we are able to make a plot just connecting both points. You mean this one?
So when this funny little drawing is, there should be automatically a cross-section generated between the points live, so we could move the points around, but we had some...
I mean, the cross-section we have it here.
Exactly, it's just projecting that somehow...
So what we don't have is a line connecting the 2 dots.
Yeah, plotting is an issue when you do live presentations.
Yeah. And basically with this, we generate the input data for the next thing that comes right now.
So we have the round of questions, I think, now for the second presentation. That was what we agreed on that, I think.
Yes, right.
All right. Yeah, maybe it's okay. Questions.
So the use case for this, do you see this as a teaching aid or something else?
So it definitely is a teaching aid, and once you dig your hands actually into it, you realize what powerful teaching aid it actually is. Because basically you can teach structural geology to a 6-year-old, and he'll
probably get it. So that's a really amazing point. We also have different things in mind. So we use it for higher education, of course. It has a really big outreach because it's just something that attracts a lot of interest. That's one of the opportunities. And of course also for us, because we actually do implicit geological modeling, for us it's really an interface. So to really explore three-dimensional data and also work with these data and manipulate it. So we can do that, and this is of course something that we will develop further for that, yes. So it's not just a toy, it's actually something that we will use in our research, yes. And right now we only show mythological data, but you can put any kind of depth information in there, so also uncertainties.
Probability and uncertainty. Most of our research is uncertainty as well, so all those blocks, all that data you could project is here.
Yeah. So you showed two pieces of Legos and kind of draw a cross section. Could you actually draw like an arbitrary line through multiple? So maybe you have 5 or 6 different levels and could extract, kind of a bended V-point arbitrary line, or is it kind of limited to objects?
As we have it now for the section is only with 2, but there is no reason why you cannot make as many sections out of it. So basically the only thing that we extract with the Lego blocks is the XY coordinates. After that we just interrogate the modeling tool that we have, which is modeling geology, and we just kind of recompute a 3D model and we ask in these new coordinates which are the methodologies. Basically, the only thing that you need is a 2D array, well, any dimension X, Y, and Z coordinates.
You need enough Lego blocks, and that makes sense.
Yeah. 3 more Legos. Thanks.
All right.
So far we don't have any solution.
How easy is to change back to topography? Change back to topography.
So guys, Sandbox Seismic have stolen the microphone, and that'll be the 6th presentation before we take a break.
If you think that it's too difficult, don't. I think it's too risky.
We don't show it anyway. Is it okay?
Okay. Yeah. All right. Okay, then that's true.
Okay, so this is, I won't say it's mandatory, but it was preferable to do this presentation just after the first one, because we used the output of those guys as our input. So we wanted to use this technology, the Sandbox, as a pedagogy, but also concurrency tools around wavefield modeling. So what we used was the output of the Kinect, computing the depth of the sand to shape the velocity model profile in 2D. And we use the different automatically detected objects as interactive structure of the wavefield imaging. For example, the circles will become sources, so you can put sources, many sources where you want, and the other object basically are receivers. So we designed this tool, keeping in mind that it would be a good pedagogic tool, but it's also very powerful to see the effect of having multiple sources, diffraction imaging, blended acquisition, because you can record receivers everywhere and see the effect on the complex velocity model profile that you can interactively modify just with your hands. I will let Yuri explain to you a bit more functionalities.
All right. Hey, Yuri, part of this geophysics group. So I'll just briefly repeat what we did using some visual aids. So basically, the idea is twofold. One is we take the topography's input, we take the objects which are recognized, we use topography's velocity model. This was motivated by a recent post by Matt on Agile blog with orienteering, where you're running depends on the topography, right? So this is a neat way to convert the topography into velocity. Then we do seismic modeling, where our velocity model is topography, and sources and scatters are basically defined by Lego blocks. So the idea is to get snapshots and project them back on top of the sandbox, and ideally that's what should happen. So you can notice some things going on here, and this is where not circle Lego blocks should be located with the diffractor, and all the circles origin points are the Lego blocks, which are sources. So unfortunately we cannot project it there, but that's a short step. Yeah.
For tomorrow.
Then the second fold of this project, as you guys already said, you have a geological model which is preloaded, cuts through it with topography. You use Lego blocks to define sources and receivers now. So now you cut a 2D section of the geological model. You do the same with the velocity. So now each lithology has a velocity value. Then we do the same seismic modeling now in 2D section. And here we have snapshots and also the recordings, which we ideally wanted to display on the sites, but again, it's we can't do everything in such a short time.
So you took the phone out. Yeah, that's another. So, but the idea is in the slides that we did previously, yes, with the two sources, we also ran the simulation this time in vertical instead of horizontal. So,
display recording. So I think that's it.
So you're doing, so topography is feeding into your velocity model. How are things like lithology, phase sheet, saturation, actual properties of the rocks, are those going in there now, or are just kind of some flat assumptions made? And if so, do you have any plans, would you extend to the rock properties ultimately to get a better velocity model?
Okay, as I mentioned, these are two different ideas, and one is similar to orienteering. When you run and your velocity of your running depends on if it's swamp or if it's you're running uphill or downhill. So topography here is an attribute to calculate the velocity. We don't have any geological model at this point. It's purely educational. So you shape topography, the velocity changes based on the different. When you have a geological model there in the sandbox and you do cross section, then you actually can build on top of it. You define the velocity as a function of any parameters you want, saturation, lithology, whatnot. Yeah. So these are two different things.
How did you synchronize with the other team? You just trusted them, or you came out like 5 minutes ago, or how do you synchronize throughout the 2 days?
We worked simultaneously all through, so we had like meetings where we discussed who's doing which part and making each different program. So we were doing most of the modeling and then discussing the code, helping with the code in different sections. So we were very much interacting. So everybody knew what everybody was doing.
The features in parallel, we did it all together. And then now when we were trying to put all what we developed yesterday, we ran out of time. So not all the features that we have developed during this weekend, as we presented here. Some of them, the logic is done, but it's not the way to do the tagging because it's quite complex.
So everything is almost finished, but it's only the merge that didn't come through in time.
Okay, and the judging is open for Team 6, so crack on, submit your votes and make a difference. We're going to take a short break now, so there's beer. I think there are a few croissants left, and take 10 minutes, and then we will start up again at 25 past again. Thank you very much.
When we had the music on.
Okay, guys, we're going to get started. And take a seat. I'll go to the back room. Okay, we're starting up again, please. Come through.
Okay, ladies and gentlemen, if you can take your seats again. We'll spin the wheel and see who's up next. So the next team is the GeoClusterFu. They definitely get the prize for most innovative team name.
Okay, hi everyone. We're GeoClusterFu, and we're looking at clustering of geochronology data. So geochronology data is something that's been pretty dated recently. It's expensive to accumulate, so it's not very high data volume. So people who like playing with data don't really get particularly interested in it, and consequently, I think it's a little bit behind on quantitative analysis and that sort of thing for that reason. So we as a team wanted to have a look at maybe making new visualizations and ways that we could cluster different types of geochron data. So I'll just jump into some silly example of how it works. So essentially you have rocks that are made up of age distributions, and by understanding the distributions of ages in rocks across an area, you can get an idea of provenance and other geological information, which is used in mainly academic research, but it's also used in the industry. So it has got some actual industry application as well, potentially. So what we wanted to do is build a reactive web app, which was something none of us had ever had a go at before. But it seemed like a really cool way to be able to help people who had no way of, accessing this information before, and be able to do really quick analysis and useful things with it that might be novel and hadn't really been seen on this kind of data before. So we were using a platform called Dash, which is something made by Plotly, which is a Python wrapper thing with some JavaScript. So basically we didn't have to do and learn any complicated web design stuff, but we could jump straight into it with a bit of Python coding. And together by sort of learning through the weekend, we actually managed to just about come up with something. So I'll hand over to Felipe now and he'll.
all the way down here. So this is the web application with. Can you hear me? Yes, you can. So here we get some description here. It's very simple. I'm not gonna spend too much time on the science because then I already did that. So very simple. You can take your data, just drag them up. You will get your data frame here nicely loaded. You just need to be careful and format the data in the right way, so you get latitude, longitude, distribution property, and so on. Then what you can do here, now this is where you do the chronology clustering. This is just work in progress, so you can only apply as algorithm agglomerative clustering. And here on the right, you have a slider. You can choose the number of cluster. We can start with a smaller one here, and you see here like the data which were shown before in the data frame. What you can do here, something nicely here, is take advantage of the powerful existing Dash library. You can do some selection here, and they'll be plotted below here. And then you can see. You can see here another cluster here, and then if you want to see what happens when you have like more cluster, you can just keep doing the same, and then you can just go here and see exactly which are the row of the columns of the data frame that you were analyzing. Just to conclude, step forward will party, and there's our pickup line is making your GeoCluster less. I think we can just wait 15 seconds.
Yeah, final point is I've probably got 5 seconds. We only have one little data set here, but one of the benefits is people can throw in data sets from many authors, chuck them in as CSVs, people in academia who've never really had the ability to use these tools before, and start sort of and understanding like hidden things and meanings in their data.
So I have a question. How did you spread the work across the team? How were you set up?
First, we divided the team into 3 parts. So first was the importing the data and structuring it in the data frame so that we can use it for plotting. So we 3 of us started doing that. Then the second part was the age density distribution and the plotting of the maps and the map services in the map which we are seeing, the clustering, and then the agglomeratic clustering, which I think Philip and Francio and Dan did. Then today morning we sat back and started marrying all those codes which we had in silos yesterday to one big code and debugging them.
A lot of the time it was everyone together, trying to figure out. We went along. So yeah, very good learning for.
Okay, voting started for Team 7. And the next team will be the Smart Dogs. This might not be spelt quite right. The writing on the wall was a little bit ambiguous. But
All right. Is it working? Yeah. Hi, everyone. Our team is the Smart OGs. We are very excited to present today the results that we have come up with over this weekend. So to introduce our team, we have Johannes, Björn, and Georg, who are working together in Germany in a company called Giga Infosystems, working with app development and web design. Brian and myself are geologists, currently working on virtual outcrops. For the German guys, it's their third hackathon, and for us, it's our first. So it's been very exciting to be part of this event, and really a lot of cool stuff to learn. To our product, which is an app that projects geological models onto a surface, in this case, the floor of this room. As you can see, it works on multiple screens at the same time. So the user experience is shared. It's also interactive, so if you use some of the attributes, for example, like rotating, it will do so in all of the devices at the same time. And now Björn will give the details.
All right, thank you very much. So the technology that it took to put all this together is almost invisible, and that's why it's all in the back end. what we got is Firebase, a service by Google that's used to synchronize parameters over all different connected devices, whether it's mobile, if it's web, if it's the desktop PC, whatever. And then on our smartphones, on our Android and iOS devices, we actually used ARKit and Google's AR Core to make the air magic happen. And without further ado, I'm going to show you a little video that we took and play right here and just explain what's happening while going along. So at first, we will step aside, and we have to join a session. So there might be multiple sessions that hold different geological objects, but what I will do, or what this phone has done, the only thing is actually place a model down there. In the back, you see Johannes sitting on his laptop, and as soon as I plotted down this huge model, he will use a scaling tool to scale it down towards the table so that we can see it a little bit better. So what that means is, or what we talked about, is the state of this model is synchronized between all different devices. That means you have multiple iPhones, multiple Android phones. As soon as I plotted down this model, Georg on the other side with his other phone is able to see it as well, in this exact same position, exact same rotation, exact same state. And I think he was complaining a little bit because you can only see the backside. So the next thing is that we will do is rotate them all around the axis so that he can get a good look at this as well. But now I'm upset, obviously. So I'm going to start going around this table and have another look. And you can see that it is a 3D model in space. You can go as close as you want, as far away as you want. You can inspect every little bit of it and really have this 3D immersion. And as we said before, this gives a whole new perspective to looking at 3D geo models. And this is only one type of model. We had plans to show models that visualize horizon borders, faults, maybe seismic cubes. There's so many possibilities to just throw down a model on your table, walk around it, and gain a whole new perspective. And that's it from us Smart OGs. Thank you very much.
How much data are you processing?
Do you mean
or using, or
storage-wise?
Yeah.
Or, I think you can say something for this.
Well, I can comment on the size of the model itself. That thing is initially close to a gig, and I had to really downsample it quite a lot for us to actually visualize it. And I had to rebake textures onto it, do lots of fancy work in Blender. But I mean, I guess it can take up to maybe a 500 megabyte file, that's including the textures as well.
What format is the file? The original model?
The original data is a point cloud PLY file, but that takes wavefront OBJs. it takes a bit of funny finagling with textures with that one.
Maybe a stupid question. Where do you see the main applicability of this app?
Well, as an academic, I see it as a teaching tool. So I can take that digital outcrop model, and before I take students into the field, I can say, have a look at this. What do we see in it? What do we not see in it? They go to the field, and then when we come back from the field, all the students can then look at the same model, walk around. They can talk about the different interpretations that they did on it. But as Bjorn mentioned earlier, we can have any type of model that you can think of, a reservoir model, seismic volume, whatever. So maybe in a meeting, everyone can sit around a table with their coffees and have a look at the reservoir model.
So follow-up question, how much of that was using existing tools and how much did you need to do yourself?
Okay, so the tools that you usually have to use on iOS and Android is Google's AR Core and iOS's AppKit. And what these libraries do is they figure out the spatial orientation of your surroundings when you go along with the camera. What we had to do is first figure out how these technologies work, and especially on iOS, because Apple doesn't like to show stuff. You have to use AR Core to synchronize the state over to Android. So I had to use ARKit in conjunction with AR Core. So we don't have to do anything of the AR stuff. What we had to do is figure out how we can share the scene between devices, figure out if I tap on the screen, where would the model appear on screen, figure out how we want to do model state, synchronize it in between devices, and then that it actually shows up. Yeah.
And a follow-up question is, you showed one model. What about if you could show different models, let's say the static and dynamic model, to co-visualize essentially 3D models?
Okay, so I have to keep this short because we're running out of time. The vision that we had is, and I think the code is in place there as well, to have multiple 3D models in one scene. So for example, I could look at a model right here, turn to the left, have a model right there. And then what is a grand vision is, for example, if I have a geological model showing different horizons, you could tap on the model, define a cross-section, then have it just show up on your wall behind you. So that's a pretty cool tool as well. Thank you very much.
All right.
Okay, so judging is now open for Team A. And Team 9 is going to be the Embedders.
Okay, all good? Let's go. Right, hi everyone. We are the Embedders, and really we're all about high dimensionality data and how do we make sense of it and visualize it. So I'm just going to talk about the high level view of what we tried to do over this weekend. Humans are inherently very bad at visualizing multidimensional data. So our aim is to come up with a way to reduce that dimensionality of multi-attribute, multi-well data. So we had an example where each well had 10 plus logs and we had 50 plus wells. Cluster that information using TSNE, which I'll go and talk about a little bit more later. And then using that TSNE result to really drive some insights into the data that we just would never have been able to do with the high dimensionality aspect of it. So if we move on. This is us as a team. We're also highly multidimensional. And if we were going to implement TSNE for us here, it would probably look something like this. We have different levels of dimensions in terms of coding, in terms of experience, and we cluster together kind of something like this. And that's kind of how the work was split as well. But yeah, moving on to the technical part.
So, do you hear me? Yes. Most people have done PCA before. It's basically looking at very high dimensional data and figuring out in which direction your data varies the most. So seismic data, for example, would be, first dimension would be in the wiggle, second dimension would probably be in the direction of the horizon, something like that. And you can see that clustering is quite nice. If you have color, now take the color away and it's a huge black blob. Here comes Disney. Disney is quite nice. It clusters. You can see the clusters without the color, and with the color you can verify that it's doing quite well. Problem with Disney is the clusters are saying what's close, but the distances between the clusters don't really say anything. So usually with Disney you say that you can't really interpret it, and we wanted to change that. This is a well. We also did it on several wells, but this is nice to see. We had 10 well logs, and we just threw them into our Disney, and yeah, it's 65,000 points and calculated clusters out of it. But well, this really doesn't say anything yet. However, this was really nice because we had data from Peter, and basically this was an oil well. And if you look over here, the brown part clusters quite well. Those are the wells that were the parts of the well that were showing oil. Now, what's interesting is because we're doing it like this, you can now choose these clusters and go back to your high dimensional data and check why there's brown in here and why there's still blue in your other clusters.
Okay, so we built an interactive web app that I'll quickly demo. So this is running on Bokeh. So in the background, it loads the data from a LAS file and it clusters it with this dimensionality reduction algorithm. You can select clusters in here. It should react, and yeah, and you can see that the well log on the side also updates, and that allows you then to interpret the data and select those points that might be interesting. You can then export the data from there, and it gives you something back to analyze maybe in another suite. So just to show what the tech was, well, we built it all on Python with AWS doing the computational part, and I'll hand over to.
Yeah, quick. So we processed the data, we built the tool, we built a website. We now need to integrate the website and the tool. We need to add more data, add more domains, and then commercialize it. So we're about our mission, ask the right questions. Now it's on you to ask the right questions.
No pressure.
We're out of time, but did you find some more oil?
That's the thing we need to look at now, right? Was that missed pay in that cluster? That's the exciting thing, right?
Maybe to add on top of that, that data set has the actual oil shows over more data points than we actually put on to that graph. So we can now go back and see and check if those clusters overall correspond to the actual oil shows. And we can do that for all the wells because it scales quite nicely. So it's a really cool technique to use for these kinds of data sets.
And the most important thing I forgot to say is that it's unsupervised. Of course, we didn't tell the algorithm, hey, this is oil there. It's completely data agnostic. We did this on wells, we can do it on seismic and other high dimensional data. Just to preempt.
Maybe just I had another question. Sorry, there was one in the back.
Just one question. You have chosen TCNet. Why is this algorithm in particular and nothing else?
To be honest, I did data exploration in the beginning, so we had kind of a pipeline flowing. Actually, kind of in the way that we're standing here, like data input, data processing, visualization, our organizer, and our geologist and our other coder. So yeah,
basically the cost function of the t-SNE is optimized to better visualize your cluster rather than optimize your data variability. So that's
especially well data can be very dirty and has outliers which mess up all the others. So I had a look at linear embedding in all versions and TCA and LSTA and MBS. All like I have the entire alphabet in my analysis. And,
Are the wells and the logs all weighted evenly, or do you have any ability to apply a weighting distribution if you felt like maybe certain wells were lacking in quality and others were a little bit stronger?
that's the beauty of t-SNE. We did some scaling on the logs in itself that with a robust scale of cycle, but apart from that, you're fine.
That's all we got time for, I think. No, it's awesome job. Nice. Thanks.
Okay, the judging has started for Team 9 now. And our next team will be On GeoLabs.
So there are data companies on GeoClusterFu.
Maybe it's a sign. Yeah.
Hi everyone. So we're going to present you like what our work of the last 2 days and on GeoLabs. But first, we're going to start to introduce each of ourselves. So I'm Pierre from Total.
I'm Chance. My background is petroleum engineering, mechanical engineering currently.
I'm Will Sanger. I do seismic data processing at Western Geco.
My name is Fernando, geophysicist and developer also.
Okay, so the idea we had this weekend, it was the following. We had this sandbox, so many of us have seen it now. And the idea was to connect the sandbox to the AR augmented reality. So you can update your sense and you see it in your 3D virtual reality. So that was the idea. And the final idea is to have the full loop between the sandbox, the augmented reality, and go back to the sandbox. Obviously, we didn't do everything. So the main goal is to go to your interpretation with your hand, collaborate, many people working together on the same data, feel what you could see, and real-time day between real world and virtual world. So the business case for that, we have today, when you look at what's the typical job of interpreters, they spend 50% of the time doing the interpretation, so meaning like interpreting, adjusting, doing some calculations, some attributes. So, and at the end, they get this kind of final maps, this RGB blend at most, but you can't really do it. So that's a basic question. How can you get something more than that? So we have seen that, so I think that's fine. You know now what is augmented reality, and we're gonna do the demo now. So the video and at the same time the demo.
We're gonna try it. Right. Glasses. I got this smaller thing.
Yes, so we basically use for the RV AR modeling plotting. We use Unity 3D that will allow us to connect with the Meta 2 data that is okay. We have a problem, so we go to the video.
That's all good live demos.
Okay, so that. You talk.
Oh, I'm gonna talk?
Yeah.
All right. So we actually did get spatial awareness with our hands with the augmented reality. You can actually walk through the planes. And you can actually, we did at the end get to zoom and scale. But I think that was, she was temperamental. She broke down at the end. So, I mean, this can happen. I think the technology in general is a few years away. I think we were putting a lot on the AR model, and I don't know how far it could go. But they get zooming and scaling.
So I think what we want to achieve now is do it with multi-glasses together, so connect all the people, connect the sandbox with the glasses. We didn't manage to do that, and then have the loop to the sandbox.
So question, how did you organize the work on, how did you break it down?
Me and Fernando got a little comfy with Unity. And it was not purposely, like, I'm sorry, we did not know beforehand when you were asking.
Next hackathon, we got
All right,
that
yeah.
Unity team.
Yes, we learned how to use Unity this weekend.
And I was making slices in Python so that we could try to render it spatially. And Pierre was also putting all this together and helping us see the big picture and planning it. And he pointed out for us the shortcoming that the hardest part is going to be getting the sand to update based on what you've got in the computer model. So our ultimate goal here was to be able to move these slices, these seismic slices, and to be able to feel the sand and use that to do geomodeling. We weren't able to get those tools all together, but it seems like there's a lot of convergence with the other people who are working here. So at some point, we think this is going to happen.
What do you think the added value is of connecting the glasses and the sandbox? What are you doing? What are you able to do with that configuration versus just one or the other?
So one of the answers is here. Picture. It's right here. So I think like you can imagine. I mean, maybe not sand, but something else. Like work on every day of geologists. They like to touch stuff. So we touch the sand, we touch anything, and we'll have people who are more comfortable with AR visualizing it. I think that can be really good stuff, and you want to have collaboration between your team, I think.
And ultimately, it's a natural interaction to be able to feel and see something that is representing a physical object.
So if you have a chance to sell it, what's the use case? Who would you like to sell it to?
Well, I work in Gulf of Mexico data processing, and we mess with salt bodies every day. And it's very hard to understand the 3D expression of a salt body. There's some pieces that we need in order to do good salt body modeling with this tool. But I think being able to sculpt in clay or for something like that, a salt body, would be a massive improvement over the workflows that we have now, where we see everything in a couple of slices. And so I think there's a huge business case to that, because we know that modeling good salt bodies reduces risk in drilling in Gulf of Mexico, for example.
And again, also we have, I think like many times, and that was part of the answer, we have trouble like being confident with what we see on this computer, so we need to see that well on something real.
Good job, guys.
In my mind, I can see that scene from the movie Ghost, where they're like modeling a salt dome in clay. Yes, that really would be geology porn, wouldn't it? Okay, here's it going to be. Voting's open for team number 10, by the way. I've noticed that the numbers are starting to tail off a tad. So do get your phones out, do keep voting, and let's have the grid Vizards up.
Okay. Okay, hi everyone. We are the Grid Wizards. We try to visibly visualize grids, of course. Our team consists of Fabian, Daniel, Jonas, and me. We are all from Giga Infosystems from Germany. We are a software company which usually deals with countrywide models, for example, in our case, Switzerland. And usually we render these grids, which we already have in some kind of database, pre-rendered, and then we have some kind of slices in X, Y, Z. Then you can exchange each position and then extract your information. This is quite cool and works quite efficiently for us, but we want to try something else. That's why we came here with a new objective where we said, okay, we want to visualize 10 million, 100 million, billion grid cells in a meaningful way, but in a browser. So this is really the obstacle, because we have like 400 megabytes per property, and we have at least 4 properties, so X, Y, Z, and then a float value. So we have like 1.2 gigabytes, which we need to put into the browser, and it's not going to crash, hopefully. And then, of course, the user should be able to change the presentation on the fly. So not like the grid, which is pre-rendered, or the slices. So our ideas were, in the first place, automatic rendering, which we then discarded after we checked it out, because it's more a medical thing, and we said, okay, for geology, it's not going to happen. In the meanwhile, Jonas is going to show our live demo, which you can also access, try out. Then we had a look at level of detail. We found out that we need some kind of structure for that in order to work with that properly. Next idea was to have isosurfaces, so to go along, for example, along the geology, which is one property of the grid, which you don't visualize here right now, and then use the other property, for example, here the permeability, and plot it on the surface, so you can go along your horizon and see that. So we didn't follow that here. What we did was using particles. This is what we see on the left side. There's a live demo in the browser working. And Jonas just dragged a GoCAD voxet into the browser, and then we parsed that thing and put it there. And that's like 400 megabytes right now of properties. And then we can do, in the upper part, some slicing. This is these controls we have over there. And we can also do some filtering for property ranges in order to reduce the amount of data. And what we found out, while visualizing quite a million of data points here right now, if we're trying to reduce the amount of data we have there, it's getting faster and better to visualize everything, and you actually can go through. Can you just show the property range stuff? Yeah, to exchange the minimum, maximum. So we have some kind of permeability, which was provided by Swiss Turbo. And then you can see, okay, we just reduce on the fly everything else in the browser. And that's pretty neat, actually. So, yeah, we also had some kind of problems. I already mentioned that when trying out some things. And yeah, that's it, basically. Thank you.
So the traditional organization, how did the question is, how did you set up as a team? You're just 4? It's just 4 of you?
Just 4, yeah.
Okay. How did you share the work and split the work over the 2 days?
So we're using in the backend actually Free.js,
and we never worked with Three.js, so we had to try it out. And the first place was to get going some GUI to drop the data on, then parse the voxel data into something we can use on the web. Then everyone was trying different approaches that I already mentioned to do the research for volumetric rendering. And we do that with Three.js. How does it look like? Level of detail, what do we need, and can we achieve this within the left hours? So, and then basically we put everything together in the end, and it finally worked out.
So how much bandwidth is needed between the client browser and the backend rendering infrastructure?
Nothing, it's everything in the browser.
Sorry?
Nothing's everything in the browser.
It's local only right now.
It's local.
Right?
Oh, it's all running locally?
Yeah.
Yeah, so for now.
Okay.
There's this, I mean, in general, our background, we could do that also with a backend and then reduce the amount of data. But our case here was to try it in the browser with this amount of data. And that's what finally worked out. So what actually, can you show it? We just dragged the file into the browser. So there's nothing transported. I mean, it's hosted on AWS right now. But as you can see, it's 400 megabytes. It was like in a second there. So there's nothing transportable in that.
It's about 5.7 million points right now, and they're working quite nicely. It works up to maybe 20 million on this hardware. But if you have better computers, you can pretty much, I guess, get to the 100 million or maybe 500 million. Not sure about that though.
So sorry, I might maybe ask the question. Where's the web server?
AWS.
AWS.
Well, it's
Is the
just
client's running here.
But it's providing just the GUI. Just
right. Okay.
So you could
so everything's happening client side.
Yes.
Okay. Thank you. Sorry. Okay. So voting is now open for Team 11. I guess the RGB Explorers have realized that there's a good chance that they'll be last, but we'll just check. Okay, I'll hand over to the RGB Explorers.
All right, thank you. So the quick introduction, I'm Florian. I'm a PhD student at DTU here in Denmark, working on seismic geomorphology.
My name is Gijs. I'm a seismic interpreter in a consultancy.
Tom Sanderson, geologist. I'm Thomas Gazola, and with Julien Cabra, we are IT project manager in Total on system.
I'm Steve, and I'm a developer on signal processing.
Excellent. All right, so we are the RGB Explorers, and our slogan is getting beyond the pretty pictures. Okay, so what do we mean with RGB blending? On the left-hand side, you have a seismic horizon with seismic amplitude projected upon. It's very difficult to really grasp what is the geology behind this. One of the techniques that you can do is you can blend in multiple frequency cubes, in this case spectral decomposition, and in these different channels, you put those cubes, and all of a sudden the geology comes out. So that is a very different way of displaying the data. But you do this before. First you do the seismic data, and then you start interpreting with well data. And so that's the kind of the normal way that we do it. So we have a pretty image, we tweak the seismic a lot to get the right frequencies out for our zone of interest, and then we start comparing it with well data in order to understand what's happening. So now what we would like to do is take it the other way around. And we start actually with the well, and we investigate the frequencies. We see what the frequencies are in the well, in RGB, and then we check what is now the best frequency to use in our zone of interest. And then we make the step to the seismic, where we do the spectral decomposition. And we made an app to do this, and Steve will give a demo of that.
So we did a lot of work and set up a workflow in GeoClusterFu notebooks to get spectral decomp running. on the well and on seismic. And then this web app represents a little part or some of those steps and it's sort of illustrative. So on the left, we took a well, we took the AI response for that, and then we computed an AI scale space here, going from the highest frequency through to the lowest frequency. And then we used the same scale space expansion on the seismic, so the same wavelength, etc. And we started to produce a colored RGB well. And the web app has a flash back end with that can compute the frequency decomp on the fly for both the well and the seismic. You saw both changing there. And we can also scroll through and look at the volume. The Z dimension doesn't quite line up here yet. So this is a section from the well that corresponds to that area in the well, and it ties over there. And what we'd hope to see is some section on the section actually matching the colors, but we still have a normalization problem. Get pretty pictures. Sometimes packages do a lot of tweaking and scaling and clipping, bring out the colors, and we have to get that to match, well domain and seismic, and we're not there yet. That's next week.
Yeah, but it is turning it the other way around. So trying to use the well and see what kind of in our zone of interest is the right blend to take instead of doing this trial and tweak that you do normally at present with spectral decomp. So in this way, it's a bit more of an educated guess, and using also directly RGB logs with the seismic, and that's also how you can compare probably lithologies with the seismic response. Thank you. Any questions for us?
How did you carve up the work between you all?
Yeah, we have quite a mixed variety of backgrounds. We have some geoscientists with not a lot of coding experience. We have some coders with not a lot of geo experience. And in the end, Steve did most of the front end, and we divided the back end, providing the input, doing the well logs, Tom providing the input, images, and so on, and making all the endpoints meet and the APIs and everything.
Yeah, Thomas and Julian did a lot of the back-end server, the actual stuff that's running and serving the images back. It was great that we were able to work in Jupyter notebooks. Some folks just prototyping code and then plotting that out. So there was a lot of interaction back and forth on that.
Did you prepare a lot for the event, or was that all achieved within the last 2 days?
We started talking on Slack a week ago, but we didn't have any code. We picked our data and brought it along. And you generate some blends and RGB blends and other stuff, but we didn't use that.
And you only arrived yesterday at 2 o'clock, so and you only arrived at 2 o'clock yesterday.
Does this have wider appeal? It's not, you don't really need the visualization once you've got the right blend. Well, then the inversion algorithm or some other part of seismic processing.
Yeah. We had loads of we had loads of ideas. This was the idea about calibrating, but what as well is instead of just an acoustic impedance and scale space, what we start upscaling other properties and then trying to figure out how to use the colors as we go along. Because now, because here you see things pinching up, see where blends, see where 2 events go into 1. It's interesting to be able to reach maybe below seismic resolution and guess what the colors.
We had plans to do proper optimization, as in not just visually see what stands out, what frequency combination stands out, makes our zone of interest stand out, but just maybe quantify that.
Thomas was really keen on the start having our optimized button, but we didn't have enough time. We'd used the scale space on the seismic to try and figure out what are the best frequencies to show what's the optimum blend for this slice of the well to show the feature. So, lots of ideas. Visualization.
All right, great job, guys.
So, ladies and gentlemen, that concludes all of the presentations. Please do get voting for team number 12. your scores will make a difference. And if you don't vote for team number 12, that means they'll all be able to rate themselves really highly, and that will bias and affect the judging. The judges are now going to go off and make some deliberations. And while we're doing this, we have a guest speaker to do a short presentation for you. So Yuri, you're around somewhere? Yuri's going to do a short presentation, and if the judges will join me on the ground floor, we'll complete our work.
Hello. Great. So yes, I met most of you folks, but so I had a defense 2 weeks ago, and my subject of my PhD work is very much theoretical, so lots of formulas. But I'm a visual guy, and I wanted to, yeah, just put a cherry on top of the cake at the end of the defense, and I came across a ARGS library available on GitHub, which is built on top of 3JS software, 3JS JavaScript library for visualizing 3D objects, things like that. And then I got interested, so I involved myself in sort of a pre-defense hackathon back in Norway. And here's a demo of what I'm going to show you now. I have these papers here, which you can play around later. I'll just leave this file here, and I will demonstrate it on my phone, but you can do the same things on your laptop, phones, whoops, everything that has a camera and, I guess, relatively modern software. So this is, this link, by the way, is on the piece of paper. So that's a GitHub page I made for my defense. So now back to like heavy theoretical stuff. I work on seismic anisotropy, and seismic anisotropy is, well, basically a situation when in rocks, waves propagate with different velocity along different directions. Okay, so we all know that sound propagates outside omnidirectionally as a spherical wave, but if we would sit in a crystal and shout, it would not be a sphere anymore. It would be something more complicated. Here I illustrate it with this complicated shape seismic wave is propagating. It's not like this is homogeneous medium, okay? So it's not because the velocity is different or densities are different. It's just inherent property of crystals that we have down there. So we describe two different velocities in seismic anisotropy. One is phase. That's how the actual wavefront propagates. This blue, and group is the actual energy propagates. So if we think about the wavefront or the wave, it won't go like this, it will go something like this. So it's really weird and it's complicated, mathematically heavy. So what I'm going to show is surfaces for phase and group velocities. And before I show surfaces, it's a little test. Just a hello world in the button up there, just to test the functionality, right? So now I can move the phone, and I can move the piece of paper, which will move the object, okay? Let's move this aside. So here are two models. One is simple, one is super complicated. If I look at the phase velocity surfaces in a simple model, allow it some time to load. So instead of having one S wave in anisotropic world, unfortunately we have two. That's actually what we have with light, which propagates from crystals as well. So that's phase velocity. It's not a circle at all, huh? And I think this AR is a neat way to actually get an idea of how complicated it is. Wait, but now the group velocity or group surface is what actually, whoops. Whoops. Group velocity is what actually more interesting. So it's also low. And so you see, it's not a circle at all, but it's not even a one piece of surface. It has kinks and folds, and that's what we actually expect to see in real data. So if we jump to more complicated stuff, I really doubt that it is possible to encounter things like that in real world outside crystals if we use lasers to study crystals. And this was phase, and if I show you the group. So each model is about 5 megabytes, so it's really ugly. But that's what our crystals have their properties. And anyway, so you use your phone, play around with it. There's a GitHub repo, you can find link to it. And I think that it was this guy, I think he's from Ireland, developing ARGS, which is a JavaScript library for AR. I came across on Slack. And yeah, it's pretty cool. So
awesome. Thanks for showing us.
All right, everyone, you are off the hook for probably at least 20 minutes. We'll come and round you up. There should still be some refreshments in the back room there, so feel free to mingle, refresh, go for a walk. See you soon.